Welcome to another episode of Mustang Physics. Today's lesson is about wave, just an introductory lesson. Lots of vocabulary you need to learn today. When you're done with this lesson, we want you to know about three kinds of waves and what it is that determines what kind of a wave is. We want you to know a lot of words: transverse, compressional, torsional, medium, oscillates, propagation, lots of vocabulary words you need to listen to. And we want you to become familiar with a PhET simulation so that you can do a lab. So let's jump into it. First off, what's a wave? A wave is simply a transfer of energy without a transfer of mass. So sound and light are waves. And what that means is that we can transmit information by transmitting a sound wave, and the energy that the sound wave carries, or the energy a light wave carries, can transmit information without actually having more stuff. In order to hear someone, the sound transmits through the air, for instance, but you don't actually end up with any more air than you started with in your ear. So waves are a way to transfer energy without actually transferring stuff. Unlike, say, gasoline, where to get the chemical potential energy, you have to have a transfer of mass. You have to buy the actual gasoline. Now, there are three kinds of waves, and they are named transverse or compressional, which is also known as a longitudinal wave, and a torsional waves. And what separates them is how the medium oscillates compared to the direction the wave is traveling. So let's deal with some of those words right now, and we'll deal with them in terms of a transverse wave. So we're going to deal with this first one here. A transverse wave is a wave where the material that the wave travels through, that is the medium. So you want to make sure you remember that word. The material through which a wave travels, that's called a medium. It oscillates perpendicular to the wave's propagation. In other words, think about a surface water wave. The surface of the water goes up and down, but the waves travel sideways. Since that's perpendicular, a surface water wave is an example of a transverse wave. Now, the wave propagation is just a wave specific term to mean that waves spread out, and the direction of the propagation, you could think of that as the direction of the wave's motion, but not necessarily the direction of the medium's motion. As a wave travels sideways on the surface of the water, the actual water itself doesn't all go sideways. Otherwise, we'd end up with all the water on the beaches and the oceans would be empty. The water itself goes up and down, and there's a little bit of circular motion that goes along with it too. If you've ever been in a wave tank, you know that you bob up and down and back and forth a little bit as the wave goes by. Now, a second kind of wave is a compressional wave. A compressional wave is like a sound wave. A sound wave and all compressional waves, the oscillation is in the same direction. It's parallel to the direction that the wave moves. So if the wave were moving to the right in this demo, if this were a slinky and the waves were going through it, the slinky, any one part of the slinky would oscillate left to right, left to right, left to right. By the way, let's talk about that word oscillates, by the way. It's a little different than vibration. Vibration means random. Oscillate means pattern. So think about an oscillation as a vibration with a pattern. So if you took a molecule of the slinky here, it would go back and forth and back and forth and back and forth in a pattern. Now, these two kinds of waves are the most common kinds of waves, and so they're oftentimes simulated. Let's go to the PhET and take a look. So this is the lab that you'll be using today, the interface called Waves Intro. And if we look at water waves and we go to a continuous wave and we turn them on, from the top, the wave might look like something like this, different shades depending on whether you're looking at a crest or a trough. But from the side, the wave would look something like this. Like most waves, the amplitude, that's like the height for a water wave, and it's one measure of the energy of a wave, decreases as the wave spreads out. The further the wave goes, the shorter the wave gets because the energy of the wave is decreasing as it spreads out into more space. Now, this is modeled as a transverse wave. You can see that the surface of the water goes down, up, down, up, down, up as the wave travels left to right. Now, when you do the lab today, you'll be able to pause this. You'll be able to grab out a measuring tape. You'll be able to grab out a graph so that you can see the water level. And then as you run the simulation and adjust the frequency or the amplitude, you can make measurements over here. Now, if we take a look at the sound wave, so let's go down to the bottom here, and you can see you can choose sound. This is a very different kind of wave. So as we push play here, there we go. The little green button turns it on. Again, if we just visualize what the waves look like, they might look like that. But sound waves are actually transmitted through collisions of air molecules. That's why there's no sound in space. There's no material to carry the wave. So as the speaker cone goes out and in and out and in, it collides with air molecules. This is obviously shown way slowed down and with much larger air molecules. But the idea is that the air molecules are colliding into each other, and it's where the air molecules are colliding that actually gets transmitted as a wave. There's no more air molecules off to the right than there were off to the left. This is an example of a compressional or longitudinal wave. If you watch any one particular molecule, it vibrates back and forth parallel to the direction that the wave travels. All right, let's head back to the notes here and learn a little bit more. So the last kind of wave we want you to learn about is a torsional wave. In a torsional wave, the material twists around the direction of the wave propagation. So if the wave is traveling down the length of something, it's transmitted as a twist around that. This often happens in man-made objects like the drive shaft of a car. It transmits energy down its length, but it's not like there's extra drive shaft at the end. The twist is transmitted down the length of the drive shaft. We don't typically think about that as a wave because the wave travels so fast that we assume it's instantaneous, that the engine twists one side and then that twist immediately twists the wheels. But in fact, it travels as a very fast waves. Now, a really famous example of a torsional wave like this is the wave that happened on the Narrows Bridge in Tacoma, Washington in 1940. This link will take you there, but I'll show you a little bit of it right now. So this is the Narrows Bridge. These towers were actually reused for a new bridge. This one fell down, and we push play here.
New mode appeared. Rather than ripple, the bridge began to twist. A wind of 40 miles per hour is not too strong, but it's strong enough to start the bridge violently.
So you can see down the center, the bridge is actually going up and down. It's at the edges. So as the bridge is twisting, it's a torsional wave that's being transmitted. This bridge is being oscillated in much the same way that a guitar string, or excuse me, a violin string would be if you dragged a bow across it, only the wind is causing the oscillation instead of a bow. We'll talk more about how strings work and how this bridge is a lot like a string in a later lesson. All right, back to the notes. So what is it that determines these three kinds of waves? Well, it's the direction of the wave motion versus the direction of the medium's motion. Let's review. If the medium oscillates at a right angle to the direction the wave's going, it's a transverse wave like light and surface water waves. If the medium oscillates parallel to the direction the wave travels, it's a compressional or longitudinal wave like sound. And if the material twists around the direction that the wave travels, it's a torsional wave like the one you just saw in that bridge. Now, on paper, we represent all waves as transverse waves because how else could we do it? So on paper, when we draw a transverse wave, let's talk about some of the names here. The crests are the peaks of the waves. The troughs, I know that's a weird way to pronounce that, but that's trough. That is the bottom of each wave. This line here in the middle represents, if it were, say, water, where the surface of the water would be if there were no waves. It's the equilibrium position. It's for sound, it's the pressure that's in the air normally. For a wave in a slinky, it's how stretched or compressed the slinky would be if there were no waves. The amplitude represents the height of the crest and also the depth of the troughs. Obviously, if waves are taller, then they carry more energy. The wavelength is measured crest to crest, but notice trough to trough is the same measurement. Be careful with equilibrium to equilibrium. If you measure where the equilibrium is going from bottom to top, you got to go to where it's going bottom to top again to get a full wavelength. So here to here is a full wavelength, where here to here would only be a half wavelength. All right, so regardless of what kind of wave we're actually talking about, on paper we'd always draw it this way, and we represent that the crests for a compression wave just represents the parts of that material that are compressed, and the troughs represent parts that are rarefied, in other words, stretched out. For torsional waves, the crest would represent the material twisting one way, and the trough would represent the material twisting the other way. Now, that gives us a common language in 2 dimensions on paper to be able to draw waves. Let's talk about some of the things that we can measure within a wave beyond its physical size, both in amplitude and length. Another thing that we can measure is the timing. So waves have a certain frequency and a certain period. So frequency, just like it was for circular motion, is how many repetitions per second. So in this case, it would be how many waves per second. The frequency would be 1 over big T, the period, the time. It's measured in hertz oftentimes. That's 1 over seconds. Now, the inverse of that is simply period, how long it takes for one wave to occur. That's often measured in seconds. Let's go to the simulation again and see how we can measure period, and then of course we could calculate frequency if we wanted to. So back to the simulation. If we measure period, we can simply bring out this graph. Now, what it measures on the y-axis is different depending on the wave. For this wave, it measures the pressure, and you can see that the pressure is high in the compressions and low in the rarefactions. So if we let the simulation run a little bit, this is with the sound wave, you can see that it tracks out the difference in pressure versus time. If we pause it, at a moment where we can see 2 peaks, we can get the period of this wave by estimating, since each one of these blocks represents 1 millisecond, this peak here to that peak here would represent, well, this is at about 0.6 milliseconds. This would be 1.6, 2.6. It's about maybe 3.5. So the period here would be about 2.9 milliseconds, the time between here and here. So that's how we can measure period in here. To measure wavelength in the simulation, we measure it between these 2 orange plus signs on the measuring tape. This is useful if we turn on both the waves and the particles. We can visualize it a little bit better. And so we can drag this measuring tape out, and we got to make sure we're measuring parallel to the way the wave is moving. So if we were up here, we'd measure the wavelength this direction. If we're right down the center, we'd measure the wavelength this direction. So I'm kind of the center of the black wave here. Again, remember, it's this little orange plus. And the center of this black wave here, that little orange plus. So these waves are about 102.1 centimeters long. Now, obviously, this simulation has got to be scaled. So it shows you what the scale is here. This is about 50 centimeters, and it gives you handy unit conversions. You can see that the millisecond that the graph is in, it gives you the metric prefix. Milli means 10 to the negative third, so that you can make metric prefix conversions before doing any calculations. Now, if we go back to the water waves, we can see that this graph shows something different. This graph shows the water level. So it's measuring the amplitude as the height of the water. The lengths of the waves would be able to be measured with the orange plus. Again, we can go from like the height of one wave to the height of the next wave, like that. So if we set the amplitude to maximum and the frequency to the midpoint, we'd be able to run the lab for a little bit. Anytime you make changes to frequency or amplitude, let it run a ways. And once this graph stabilizes, it means that you're measuring waves that were made with that frequency and amplitude. It takes time for those waves to pass by the sensor. Then you can pause it. You can get the wavelength like this. You can see it's about 2.7 centimeters. We can get the time by measuring between peak to peak. And you can see it's about 1.6 seconds or so. And then we could use that to calculate the speed of the wave, since we know how far a wave moved, one wavelength, in the amount of time it took to move one period. That brings us back to our notes. Let's take a look here. While the speed of a wave is physically determined by what kind of wave it is and the properties of the medium, we can calculate that speed using the wave speed equation. Speed is wavelength over period. Now, before we get into the nuts and bolts of this, let's pause for a moment. Let's make sure you understand the distinction here. So, light, regardless of how we might calculate its speed, has a particular speed as it travels through a vacuum. It's about 300 million meters per second. Light's generally faster than sound, which is generally faster than surface water waves. That's because light is just intrinsically a very fast wave, and sound is intrinsically a faster wave than surface water waves. So the speed of a wave is actually determined by, first off, what kind of wave is it? It's also determined by the properties of the medium. So for instance, if you use contact lenses or glasses, light actually travels slower as it goes through the contacts or through the glasses, and that's part of what makes it turn. More on that next time. So the speed of that same kind of wave, if we take sound, for instance, is different through different materials. It travels 340 meters per second in air, but almost 1,500 meters per second through water, and even faster through solids like steel. Now, within the same material, different types of waves can travel at different speeds. So the compression waves usually go faster than transverse or torsional waves. So I want you to understand the physics behind what determines the speed of a wave is what kind of wave is it and what's it traveling through. Now, if we don't know what that speed is and we want to find it, we can measure wavelength. This is the Greek letter we use to represent wavelength, lambda, over period, or we can do wavelength times frequency, since frequency is the inverse of period. In today's lab, we'll do wavelength over period. So an example of how to do the lab appears on the next page. All right. So let's say once you've opened up the waves intro for yourself, the prompt said something like create a continuous surface water wave with the frequency set to the midpoint and the amplitude at maximum. Observe the wave from the side and measure the wavelength and period, then calculate the speed of the wave. Well, within the simulation, you would do this. So you'd set up the water waves, you'd have the continuous wave on, you'd turn it on, and the waves would travel across the screen. At some point, you'd pause it, making sure that you've let those waves run out for a while so that the pattern on here is consistent. And then you could measure wavelength and you can measure period. Your work would look like this. Wavelength was 2.7 centimeters, period's 1.6 seconds, convert from centimeters to meters, and then go ahead and calculate the speed with the distance, the wave traveled in one wavelength and the time. So these waves are only traveling about 0.017 meters per second, or about 17 millimeters per second. The speed of water waves is actually dependent on the depth of the waves. So these waves must be in very shallow water if they're going that slow. So the lab itself is on the last page of these notes. You can see there's 12 questions, and we want you to play around with surface water waves a little bit more, then with sound waves, then with light waves, and then check your understanding at the end. All right. Enjoy. Hopefully you've learned a lot about the three kinds of waves and some of the vocabulary we use to describe all waves. We'll see you next time.